The title of this presentation is Overview and Concluding Remarks on Multiplayer Quantum Games, Parallel Repetition, and Anchoring. I'm going to provide an overview of the previous four presentations I gave in this series just to pretty much close things out, which is what I typically do, namely to just basically encapsulate a couple of the main objectives and a couple of the main arguments and how they relate to the most simple game theoretic objects that I've been describing for the two-player case and the two-player setting in the first presentation of the series. And this is pretty much given by the fact that I had drawn the attention of the viewer to the fact that in the first presentation of this series, I've been describing a couple of works from statistical physics, namely the fact that I looked at a wide variety of models ranging from the random field Potts model to the six vertex model and the Ashkin-Teller models to the Jellium model, which is related to a model of the Reese gas, as well as to Poisson structures and how that relates to quantum scattering approaches and how this can even be used to quantify the existence of phase transitions for the Gaussian free field and for the random field Potts model, or for the or for the for the lower dimension for the long range lower dimensional Ising model. And altogether, a lot of these types of objects from statistical physics were mentioned in our initial discussion because they were really trying to help us to motivate, so to speak, dependency breaking and how that relates to symmetry breaking, namely the fact that when we're looking at dependency breaking and trying to remove correlations in quantum phases of matter or quantum matter, we're looking towards some quantum version of symmetry breaking because symmetry breaking in statistical physics, it's basically breaking the symmetry or removing some type of symmetry or some type of favorable energetic property or maybe some favorable characteristics of a model. And that can be reflected upon through arguments that I provided in several of my previous works on the archive in statistical physics. And obviously, as one can expect, to make that connection or to make that conceptual leap from just some type of statistical physics perspective to some type of quantum physics interpretation or arguments, or maybe even perhaps like we've been describing computations with entropy and related types of objects. I also described these works, namely one of my earlier works in quantum information theory from 2023, coming up on 2 years ago, in which I described optimal and approximately optimal quantum strategies for XOR star and FFL games, and like how I've described at various parts throughout the presentations in this series, that basically I've been making use of just basically a couple of straightforward criteria to be able to pass to a dual game, namely an XOR star game for an XOR game, and how this actually relates to other two-player settings for the FFL game. And even before this paper on XOR star and FFL games, I'd kind of already been familiarizing myself with performing time evolution on quantum circuits because, after all, performing quantum computation over these types of classes of circuits, it's very much related to quantum algorithms and variational quantum computing, and which is an extension, like I've described in some of my presentations from a while ago in the APS April and March meetings, how this algorithm, this variational quantum algorithm, which often throughout the literature is abbreviated as VQA, it's an extension and a generalization of the variational quantum eigensolver, which is pretty much a type of numerical linear algebra problem for being able to obtain solutions to some desired partial differential equation in nonlinear problem of interest. And then more recently, in this year 2025, I've been describing also how my works from quantum strategies, error bounds, optimality, and duality gaps for a wide variety of multiplayer games, in addition to my most recent preprint from like around a month and a half ago for relating to error correction, authentication, and false acceptance probabilities for communication over noisy quantum channels. They're also relating to different aspects and different considerations, like how we've also been describing, for instance, in one of the requirements through the data processing inequality, how that's relating to just basically trying to establish lower bounds for the fidelity and for the entropy of information quantum states that are distributed over quantum channels. But of course, in this most recent preprint of mine on the archive, that's currently under peer review as well. Um, While I don't discuss exactly distributing and transmitting class or quantum information over a quantum channel, it's since still instead classical information over a quantum channel, a lot of the similarities still remain, and a lot of the aspects or the computational routines or information processing tasks, they're actually roughly similar in some cases for transmitting either classical information or quantum information over a quantum channel. And so now I'm going to again reiterate some of these type of minimalistic objects, I guess one could say, or just basically how it's relating to the objects that we've been studying throughout the presentations in this series, and how basically we're going to come to the same ending point I was at in the previous presentation of the series, namely discussing again and reiterating the optimal value, the anchored optimal value under parallel repetition for multiplayer games. And this is given by the fact that when we're performing parallel repetition, it's pretty much all amounting to parallel repetition of the question sets that are distributed to each one of the players from the referee's probability distribution, that then the referee, upon receiving the answers from each one of the players for each instance in each round of parallel repetition, is going to determine whether the game predicate is won or lost, namely whether it's satisfied or not, hence determining whether there's a very sufficiently good or sufficiently high winning probability for this particular round and instance of the game. And this is just given by the fact that if we take the multiplayer question set that are distributed to each one of the players, script q sub I, and we're raising it to the tensor power of little k, where little k signifies the number of rounds of parallel repetition which we're repeating a game, it's equal to a collection of tuples with k entries, where each one of the entries is corresponding to a question set, which is indicating 1 up to little k and q prime 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 with an arbitrary number of primes depending upon however number many of players or participants there are in a game, also going from 1 up to little k, corresponding again to the rounds of parallel repetition. In parallel repetition of the XOR optimal value, again, it's relating to this pretty well-known principle, but which I felt maybe wasn't exactly emphasized as much in the literature or approached from the type of perspective that I provided in that May preprint of mine that's also, it's currently under peer review for quantum strategies, error-bound optimality, and duality gaps, because I was pretty much looking at from the perspective of performing parallel repetition what would be the impact on the optimal value? And of course, it's a very well-known fact, obviously, that the optimal value of the XOR game after performing 2 rounds of parallel repetition, namely this quantity omega of XOR of G of XOR, where this wedge operation, again, like we've been describing it throughout the presentation of the series, it's relating to parallel repetition, it's identically equal to just omega of XOR, namely 2 rounds of one round of parallel repetition for the XOR game, which is identically equal to the product of 2 identical copies of the maximum winning probability for the XOR game, which notably is equal to half, which is not equal to 1 over square root of 2, which is the original value of the XOR game. And that's really what's stemming and relating to and informing a lot of the interests of this work, because we're pretty much determining and asking ourselves what would be some type of generalization of parallel repetition, particularly through anchored parallel repetition, in which the viewer will recall that I provided for him and her several types of expressions and conditions, whether through the probability mass function, which is given for anchored questions, or also even for specific types of conditions for alpha anchoring, which is just introducing some strictly positive parameter, which is obviously the fact given that it's corresponding to a probability. We don't want it to occur with probability 0, this anchoring probability, as well as we want it to potentially be equal to 1. And this is just given by the fact that we can anchor and remove quantum correlations, hence constituting an instance of dependency breaking for quantum information processing from these types of anchoring procedures. And relatedly, like we've been describing for the FFL game, it differs from the XOR game because the FFL game and the XOR game, they can both be analyzed within a 2-player setting, namely with 2 numbers of players. However, the FFL game is different from the XOR game because it differs in the assignment of one probability. So, namely, when we're looking at a game, we're always assigning probabilities to just basically different types of answers that any one of the players and participants in the game can provide in response to the questions drawn from the referee's probability distribution. And just given the fact, like we've been describing more explicitly in other presentations of this series, how the fact that the FFL game differs from the XOR game in one assignment, namely one probability of the player answering one question, it's 1/4 in comparison to 1/2 in the XOR game. This actually results in a significant difference in behavior of this game, namely the invariance of the optimal value. The fact that performing 2 rounds of parallel repetition of the FFL game leaves this value invariant, namely that it's equal to 2/3 and notably not equal to the square of 2/3. And we have been describing throughout other parts of the presentation of this series so that we can obtain some type of handle and some type of estimate on the exponential decay of the multiplayer anchored value under parallel repetition, the fact that there are these three complexity related results. And in general, computational complexity is related a lot to quantum algorithms and quantum information processing because a lot of people are always making and establishing various conjectures all throughout YouTube and many other venues and presentations for basically discussing whether certain computational complexity classes are equivalent and are equal. And this would be really helpful maybe in terms of quantum computing or quantum algorithms because it could maybe be, it could provide more assurance for the quantum computing industry that some next generation hardware could actually maybe one day be synthesized and built in like these types of big labs that IBM and Google Quantum AI and Quantinuum or all these other types of companies are developing, and how that could actually maybe relate to being able to perform some types of quantum computing tests and some quantum computing protocols with potentially maybe a polynomial or maybe in the more optimistic case with an exponential speedup. And so this is given by the fact that for the first complexity theoretic result, we're again describing how to determine the big O upper bound or the big of O order of some system of expected values. And in the third presentation, if I remember correctly, of the series, the third and fourth presentations of this series, I really provided a lot of expressions for system of expected values for the viewer, namely describing how these types of expectation values occur, what are the types of quantum states and how they correspond to different multiplayer quantum strategies that players can adopt for potentially, hopefully, being able to win the game by making use of entanglement so that they can win with a higher probability using quantum strategies in comparison to classical strategies. And again, the viewer will recall that in all of these big O functions, which are in these three complexity theoretic results, which are used to build up to the decay of the anchored optimal value under parallel repetition, we're having just basically ratios of some delta multiplayer parameter normalized in the multiplayer anchoring probability. And how this is actually relating to, again, all the discussions and all the observations that we've been having is that this is a different type of way to establish and to conclude some desired exponential decay or really any type of rate of decay like I've provided in the third presentation of the series, because there are many types of possible decays that can be obtained for the optimal value under parallel repetition, especially in the multiplayer anchored setting. And we can see that in theorem 2 from the system, from this complexity related function, which is provided for the system of expectation values, which is given in the first theorem. In theorem 2, the positive operator valued measurement system is given by instead being related to this type of expression, except that we're nullifying or we're decreasing the contribution of this delta multiplayer parameter, which we have been describing and we explicitly define in other presentations of this series, and we're normalizing it by a higher power of the multiplayer anchoring probability. And finally, in the last theorem, by making use of Pinsker's inequality, which is a well-known result in quantum information theory, which is used to upper bound, will provide a less than or equal to upper bound or a greater than or equal to upper bound for the L1 norm of the difference between rho and sigma, where rho and sigma are two quantum states in terms of a summation over a relative entropy, over relative entropies, we're able to obtain some other type of result, which is instead in comparison to the square root of the delta multiplayer parameter, which is given in this big of O function in the second result. In the third result, we're instead just taking a square root, but we're actually even normalizing by even a higher power, namely the multiplayer anchoring probability raised to the 2 of big N, where big N signifies the number of players plus 1 in comparison to n plus 5 in the second result and n plus 1 in the first result, respectively. So again, this is just, I felt it was really helpful for the overview in the last presentation of this series to again reiterate how we've been describing these complexity theoretic results, how inherently they relate to system of expectation values, which is inherently related in discrete probabilities, and how this is, again, we're going to reiterate how this, what impact and implications this has for the decay on the on parallel repetition of the anchored multiplayer optimal value. And so I felt that providing a reiteration of the overview slides from one of the previous presentations was helpful, namely for the viewer to recall that we further built upon discussions of quantum games in previous presentations, namely including defining sets of dependency breaking variables and how these can be used to remove quantum correlations, the relative min entropy, anchoring, and parallel repetition. And altogether, this was allowing us to further discuss how computations with entropy determine upper bounds for the POVM system and related arguments for multiplayer anchored parallel repetition. And so I just wanted to very briefly reiterate some of the two-player objects to again build up to some types of results which reiterate the multiplayer setting and how this is a generalization of ordinary parallel repetition. Just given by the fact that for the two-player game, we can look at the bias beta sub g of s being as a summation over little s and little t respectively belonging to the sets big S and big T of the following expected value, namely the game matrix, which is indexed in g of s of t, namely for the two-player setting, we're looking at a matrix where the rows and the columns are indexed and the questions are distributed to each one of the two players and the two participants multiplied by this expectation value of the bra psi of the namely bra of the optimal value of the tensor product of A of S and B of T, namely the tensor product of the tensors from Alice's responses and Bob's responses from the two typical archetypical players which are involved in the two-player games and other information processing tasks within the field of quantum information theory. And finally, we're also having a ket psi for corresponding to a ket psi of the optimal quantum state for playing the game. And the question sets that we've been describing for these two players are defined as follows: A of big S and B of big T respectively being identically equal to the union over little s and big S and also little t and big T, which is given by binary plus or one plus minus one observables, namely the fact that A of S can belong to plus one or minus one, as well as B of T can belong to plus one or minus one, signifying that these responses that can be collected from the referee after distributing questions to the players Alice and Bob can either have a negative impact, minus one, on the referee scoring predicate, or a plus one, and hence a positive impact on the referee scoring predicate. And we want to really maximize as many plus ones as possible so that the players can make use of entanglement and other aspects of quantum information for being able to win the game with the most significant or the highest probability possible. And the relationship between the bias and the optimal value, a linear relationship, in fact, is given by the fact that beta is equal to 2 times omega, the optimal value of the game, that the maximum winning probability minus 1. And we can majorize the bias because beta sub s or beta sub g of script s can be made independent of script s, namely the set of all possible strategies, by just taking the supremum over script s, in which we're just getting beta sub g. So namely, we're looking at what is the bias for some type of maybe two-player game, or even like I've also defined for the player, a multiplayer game independently for the strategy. So namely, given some instance of a strategy within the set of all possible strategies script S. And the epsilon approximality of the bias for the two-player setting is again some type of very helpful notion because it's relating to the fact that given the existence of some strictly positive parameter epsilon, we can look at lower bounding beta sub g of script S being being greater than or equal to a 1 minus epsilon multiplicative factor of beta sub g and also being upper bounded by beta sub g. And the rates of decay for the optimal value for the two-player game under anchored parallel repetition is given by the following statement. I thought that this type of expression from a decay or an expression for the optimal value that was provided in previous works in the literature that I've been describing, it was very helpful and informative to provide for the viewer because it just really demonstrates what are the types of expressions and basically quantifications of the decay of the optimal value or expressions of the optimal value that we would hope to obtain in generalizations of parallel repetition through anchored parallel repetition specifically. And this is given by the fact that we're looking at generalizations of a previous item in the upcoming paper that I'm going to submit to the archive soon for expressions of optimal values under anchoring. So this is just basically from the fact that from work of Bavarian, Vidic, and Ewan, which I've discussed and described at several points in presentations of the series, the authors of 30, namely another reference by Kundu and Jain, argued that a generalization of the anchored parallel repetition on the optimal value satisfies this form. Namely, we're looking at the anchored parallel repetition of the quantum value omega star of G twiddle sub k, where little k again, it represents the number of rounds of anchored parallel repetition. And these authors, Jain and Kundu, in this conference proceeding that I've cited several times also throughout my upcoming paper and my upcoming project, they provide this type of expression, namely 1 minus an optimal value raised to the fifth. In this bigger parentheses, they're having this big omega function, which is another complexity theoretic function that's dependent upon k, little k, the number of rounds of parallel repetition, as well as the reciprocal of the natural logarithm of the product between the answers provided by Alice and Bob. So again, this is just saying that script A, as we're denoting below, script A is a set of answers from the first player, script B is the set of the answers from the second player, and little k is the strictly positive parameter representing the number of parallel repetition operations. And again, when we're looking at these complexity theoretic results, these types of parameters or these types of quantities always come into play across several works throughout the literature, namely the size of the cardinality of the responses provided by Alice and Bob or even the size of the responses for an arbitrary number of players, in addition to the ratios k, again, the number of rounds of parallel repetition normalized in the reciprocal of the natural logarithm of the product of script A and script B, as well as psi squared k, the reciprocal of the natural logarithm of the product of the cardinalities of script A and script B, where psi squared represents the anchoring probability. And the viewer will recall that to generalize these types of results, we're looking at components to the multiplayer thresholds in the three main complexity theoretic results that were being used to obtain some desired conclusion about the optimal value. Namely, given the fact that we're still performing little k, which is the strictly positive parameter corresponding to the number of parallel repetition operations, we're normalizing in the logarithm, in a natural logarithm of the product of the cardinalities of script A sub I, namely the answers from any one of an arbitrary number of big N players, as well as also introducing another parameter, which is the anchoring probability raised to the number of players big N times the instances and the number of operations of parallel repetition normalized by the same logarithmic quantity. And we have also been describing, but to reiterate, systems of expected values without normalization. Normalization, it comes into play because we can either normalize these quantum states or introduce various normalization factors for this second identity operation, which is occurring in this tensor product of quantum operators that's acting upon this optimal state that ultimately we're taking the norm of and we're taking either an expected value with respect to the question set of the first player or expected values with respect to a distribution of a product support or of a support of a product, a product of question sets, namely script q sub 1 up to script q sub n, in addition to an expected value of r to the minus I conditionally upon the fact that we're winning across all coordinates, where again, the viewer will recall that r to the minus sub I signifies or indicates an instance of dependency breaking away from instance I. Oh yeah, and also these are just all the unitaries. The viewer will recall that we had described these unitaries script u sub 1 up to script u sub big N. And so the dependency breaking states over the number of players admits the following decomposition. Namely, we're looking at kep psi, which can be identically decomposed in terms of set kep psi sub k, where we're looking at dependency breaking among the first k players, which were the parameter k, which is an index in this union. It's varying between 1 and big N inclusive. In this system of expected values, like we mentioned 2 slides ago, through this system can be generalized to twiddle of script E, namely introducing some type of normalization for the optimal strategies for each one of the players, while keeping the unitaries for each one of the players, as well as the tensor product representations of operators the same and identical. And also given the fact that we're taking still two expectations, we're nesting expectations within each other that we're taking of this norm. And this is again relating to the relating to the fact that the viewer will recall that there are normalizations of quantum strategies, namely twiddle ket up psi is equal to ket up psi normalized by the norm of itself, which is proportional to ket up psi. In this system of expected values like we've been describing, it's pretty much coming into play because in place of this normalization, we can make use of just basically being able to introduce some different types of systems or variants of this system of expected values for being able to argue that the first complexity theoretic related result forms from which, as related consequences, we can also obtain the desired results from theorem 2 and theorem 2 for the complexity theoretic results, and then altogether be able to conclude with some type of decay on parallel repetition of the multiplayer anchored optimal value. And so again, this is being able to obtain this desired rate of decay for the optimal value is dependent upon the following two properties, namely sampleability and usefulness. Sampleability first states that there exists some state ket of big theta independent of the questions distributed to all the players, and another state little ket of little theta, which is dependent upon these questions which are distributed to each one of the players, such that applying the tensor product of the player unities to the set ket of big theta minus the state of ket of little theta is approximately 0 with respect to the L1 norm, as well as the usefulness property, which is stating that each participant in the multiplayer game can perform a measurement respectively denoted script 1 up to script big of N, such that performing a measurement on the state ket of little theta that we introduced in the previous property for the sampleability condition minus the conditional probability that the players can just basically win given that they're responding to questions conditionally upon the fact that they're responding to questions little q sub 1 up to little q sub n is approximately 0. And this norm condition can hold for all of the types of measurements that the players can provide to the state little ket of little theta. So I mean, this really shouldn't come as a surprise that measurement and extracting measurement is really coming into play, because after all, even from my first paper in the field of quantum physics and quantum computing, when I was looking at basically being able to extract measurements from wave function and cost functions that I was driving in that paper, it was really still fundamentally relating to the fact that we want to be able to extract measurements in a meaningful way from a quantum system without losing too much information when we're disturbing the system to measure it and to determine whether some expected outcome ultimately occurs. And so we had also been describing a first set of conditions, namely related to the fact that we were providing for the viewer several complexity-related theoretic results, either relating to the square root of the delta multiplayer parameter, which is given in the first two items, which again is given by some average of a summation of probabilities, which is given by the average of a summation over some probabilities for the number of players big N, as well as in these two other results given by the fact that we're providing some big O function upper bound for some other types of summation, some average of summations of probabilities. So I just very briefly wanted to flash this slide again, just to exhibit some of the intermediate types of objects and quantities and upper bounds which we're obtaining for these types of three main complexity theoretic results that I've been reiterating in this presentation of the series. And a second set of conditions is relating to the fact that we can make use of arguments which were given with respect to the multiplayer, delta multiplayer parameters and thresholds in the previous presentation of the series, namely given the fact that we can also argue that other types of inequalities hold of a similar form, in which maybe we're looking at a different power in terms of a normalization in the big O function, this complexity theoretic function, depending upon the multiplayer anchoring probability, as well as dependent upon maybe the square root of the delta multiplayer parameter. In the intermediate POVM systems, much like intermediate systems of expected values and intermediate systems of that we're going to ultimately be upper bounding with Pinsker's inequality come into play. And for instance, for upper bounding script POVM of E, which is related to the script or the system of expected values of positive operator valued measurements in the second main complexity theoretic result, we can introduce these systems script POVM E of E prime and script POVM of E prime prime, which is given by respectively in the first system, we're taking the norm of the POVM1 up to POVM of big N and subtracting a conditional probability, namely conditionally upon some instance of dependency breaking, in addition to the fact that for the next closely related system, script POVM of E prime prime, we're just taking the expected value of the previous system. And an adaptation of the three-player bound to a four-player bound is helpful because we make use of the following proposition in some of the arguments for these three main complexity theoretic results, namely the fact that we can upper bound the expected value from dependency breaking unitaries for the players, namely giving dependency breaking unitaries acting on V1, V2, V3, and V4, one has that the expected value of just basically the tensor product operation of the dependency breaking unitaries applied to the sorry, there shouldn't be a Q4 here, that's a typo, but there shouldn't be there should be applied to which is applied to the normalized state of a dependency breaking variable with all of the three questions anchored minus the phi, namely the normalized dependency breaking state with no questions anchored can be upper bounded by some big O function of delta multiplier to the 1 over 100 normalized in alpha to the fourth. And now I wanted to conclude this last presentation, the overview presentation of the series, by again describing the decay of the optimal value under parallel repetition, which is given by Theorem 4, the main result, which was provided in the previous presentation, namely the rate of decay of the optimal value under anchored parallel repetition to close things out. So just basically given by the fact that we're fixing some S multiplayer parameter, which is given by the maximum of the logarithm of the product of the logarithms of the cardinalities of the questions distributed to each one of the players, and taking this maximum with 1, taking the multiplayer anchoring probability to be non-inclusive between 1 but potentially inclusive, potentially equaling 1 for this multiplayered alpha anchored game G, big G, and as well as two parameters, two strictly positive parameters, epsilon multiplayer and C multiplayer, where the C multiplayer parameter is not inclusive between 0 and 1 over big N to the 2 to the big N log of E, then we have that the decay of the optimal value satisfies this form. I made some very slight edits from the expression that I provided in the previous presentation, but namely the fact that we're looking at performing little k number of rounds of parallel repetition, and namely the fact that we're looking at the decay of omega multiplayer of big G of bot, namely the anchored game, under little k rounds of parallel repetition is upper bounded by 10 over the epsilon multiplayer. So this epsilon per factor to the exponential decay, where the actual power of the exponential decay is dependent upon C multiplayer, alpha multiplayer raised to 20 n plus 1. So namely some quantity that's proportional to the number of players big N. But the corrections that I made to the expression from the previous presentation was that the power to which the epsilon multiplayer parameter has to be raised to a quantity that's less than whatever the anchoring probability is raised to. So I changed this to 6n, as well as correcting this contribution in the power of the exponential decay to little k. But still, this numerator of the power of the exponential is still normalized in S multiplayer, namely this maximum of the logarithm of the maximum between the logarithm of the cardinalities of these question sets are distributed to each one of the big N players with 1. And thanks for watching.